In a traditional on-premise data center, security begins with a physical perimeter. You control the hardware, the cables, and the locked doors. In the cloud, that physical perimeter dissolves entirely. The infrastructure is decentralized, distributed across a continuously shifting network of remote nodes. This creates an immediate paradox for security architects. We no longer have direct physical access to the hardware routing our data. We cannot walk into a server room to plug in a network tap or physically isolate a compromised machine. Consequently, network visibility is no longer a default state provided by the hardware. It must be actively, deliberately engineered into the architecture from the moment of deployment. To establish that visibility, architects rely on centralized logging. Comprehensive log aggregation becomes the absolute bedrock of cloud security, serving as the singular source of truth for every action taken across the environment. In a distributed cloud architecture, you cannot secure what you cannot see. If a system event, user action, or network request is not explicitly logged, it simply did not happen. This diagram maps cloud infrastructure telemetry across 3 distinct pathways. First, the control plane captures administrative actions like provisioning virtual machines. Next, the data plane records application behavior and database queries. Finally, the network layer monitors raw traffic data moving in and out. Defensive tools like firewalls will inevitably fail to block every sophisticated intrusion. When an initial attack is halted but a subsequent exploit slips through, interconnected forensic artifacts, a failed data plane login, a blocked network port scan, and a modified control plane policy. Raw, disparate logs stored across different services offer very little value. The data must be aggregated, normalized into a consistent format, and correlated to expose the actual sequence of an attack. Once an intruder breaches a network, their immediate priority is to erase the audit trail to hide their movements and maintain persistence. This diagram illustrates the countermeasure, routing logs out of the primary environment into immutable log storage. This vault exists under a separate administrative account. If attackers compromise primary credentials, they are physically barred from the secure account. With the logs safely aggregated and secured, organizations deploy a Security Information and Event Management System, or CIEM, to process the raw data. CIEM tools apply correlation rules to the centralized data in real time, achieving continuous auditing over manual reviews. The system automatically detects anomalies and alerts administrators the moment an unauthorized action occurs. Physically separating and hardening the storage of your logs is the only architectural method to guarantee the forensic integrity required for that continuous auditing. Collecting and securing data is a technical mechanism. Governance is the process of deciding what rules that data must follow. This diagram shows the risk management cycle, the framework used to evaluate vulnerabilities in a cloud environment. Architects identify potential threats, assess their likelihood and impact, prioritize the most critical vulnerabilities, and then choose to mitigate, transfer, or accept the risk. In the mitigation phase, architects translate identified risks into internal security controls. For example, the risk of unauthorized data access is mitigated by writing strict identity and access management policies limiting user permissions. Beyond internal security initiatives, external regulatory compliance standards impose legally binding rules on the governance of cloud environments. Specific privacy mandates, such as the European Union's General Data Protection Regulation, force organizations to implement rigorous data localization protocols, encryption standards, and rapid breach notification systems. Violating these compliance frameworks carries severe consequences, ranging from massive financial penalties to forced operational shutdowns. A mature risk management framework takes these abstract legal requirements and ethical boundaries and translates them directly into the technical architecture of the cloud environment. Human auditing fails at scale. A compliance officer cannot review user permissions fast enough to keep up with the rapid elasticity of automated cloud provisioning. This visual represents a Cloud Security Posture Management, or CSPM, engine. CSPMs are designed to solve the problem of scale by automating the governance process. Because it integrates directly with the cloud provider's APIs, the CSPM engine continuously monitors the infrastructure. Here, it identifies an anomaly, an S3 storage bucket misconfigured for public access. The CSPM does not just log the error, it executes automated remediation. It immediately alters the access controls, restricts the bucket, and returns the resource to a compliant state without human intervention. This methodology is known as policy as code. Security standards and compliance regulations are written into executable scripts, ensuring they are continuously enforced across every deployed resource. By utilizing policy as code, organizations eliminate the vulnerabilities associated with outdated, point-in-time manual audits, replacing them with a system that self-corrects in real time. These automated corrections generate their own audit trails, which integrate directly back into the centralized CM system to provide the security team with a complete record of the remediation. Automated governance is not a luxury reserved for massive enterprises. It is the baseline necessity for operating secure infrastructure at an exponential scale. Every concept we have covered, from immutable logging to automated governance, must be filtered through the shared responsibility model. The cloud provider's underlying architecture dictates exactly where their security duties end and where the engineers begin. This comparative matrix illustrates 3 distinct deployment models that alter an architect's security responsibilities. On the left is the private cloud model, running open-source platforms like OpenStack. The environment relies on modular components like Nova for compute resources and Swift for storage, deployed directly on bare metal racks. In an OpenStack deployment, the architect bears the total security burden. You are responsible for patching the physical network switches, securing the host operating systems, and managing the application layer. In the middle is the containerized model, using engines like Docker. Here, multiple isolated microservices operate, while sharing a single underlying operating system kernel. Because these containers share a kernel, traditional network firewalls are blind to their internal communications. Securing this environment requires specialized cloud workload protection platforms, or CWPPs, deployed at the workload level to monitor inter-container traffic. On the right is the public cloud, utilizing hyperscalers like Amazon Web Services. This is a massive, globally distributed network of managed services. Here, a strict boundary exists. The cloud provider secures the underlying physical infrastructure, the physical network, and the hypervisors. The customer is strictly responsible for securing their data, configuring their identity and access management rules, and enforcing resource policies. An architect's choice of underlying infrastructure establishes the physical limits of their security controls, dictating exactly which tools they must deploy to maintain visibility. Despite the stark differences in these varied deployment models, the universal philosophy of cloud security always remains consistent. Whether you are managing bare metal servers in OpenStack or utilizing managed services in AWS, your ability to detect threats relies entirely on engineered, immutable logging. Whether monitoring ephemeral Docker containers or auto-scaling public cloud instances, dynamic environments demand automated posture management to continuously enforce compliance. An enterprise's ultimate security posture is defined by its ability to maintain sovereign, granular control over its data, regardless of the physical server it resides on. Ultimately, maintaining a truly secure cloud posture requires the architectural mastery of both decentralized visibility and automated governance.